Bismillahirrahmanirrahim. How are you, students? Today we will start a new chapter, Oscillation. Chapter number 7, Oscillation. Lecture number 29, page 170. Oscillation. First, we will explain what is oscillation. First, we will explain oscillation, rotation, vibration, revolution, cycle. All these represents same type of motion. This motion is periodic, 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 periodic. If all these type of motions are periodic, it is called simple harmonic motion. So oscillation is the vibratory motion. The to and fro motion of a body is called oscillation. To and fro. The to and fro motion of a body is called oscillatory motion. Periodic motion. Oscillatory motion is periodic. It is called simple harmonic motion, or the type of motion in which acceleration is directly proportional to the displacement, and always acceleration is directly proportional to the displacement and always directed towards the mean position. When a particle executes repeated movement about a mean position, it is said to be in harmonic motion. And if this motion is repeated at regular interval, it is called periodic motion. For example, the motion of a spring, of a mass attached to a spring, simple pendulum, or the back and forth motion of a swing. Now we will discuss different terminologies related to simple harmonic, related with simple harmonic motion and oscillatory motion. So oscillatory motion. First, we will explain vibratory motion. Vibratory motion is the to and fro motion of a body is called vibratory motion. I will explain time period. It is already explained. Time period is the time required to complete one vibration. Time period is represented by capital T. By capital T. Time required to complete one vibration. It is the duration of time. Duration of time per one vibration. Time per one vibration. Next is frequency. Next is frequency. The number of vibration completed. Number of vibration completed in 1 second is called frequency. The number of vibration completed in 1 second is called frequency. Now oscillation. These are the example of oscillation. Now another thing, amplitude. Amplitude is the maximum displacement. Maximum displacement from equilibrium position. From equilibrium position. From equilibrium position. Angular frequency. Angular frequency represented by omega. represented by omega, angular frequency. The number of revolution per second of a body is called angular frequency. Number of revolution per second is called angular frequency. Now oscillation. Oscillation is the repetitive variation, typically in time, of some measure about a central value. Central position is called mean position. Between two or more different states, the term vibration is precisely used to describe mechanical oscillation. Familiar examples of oscillation including a swinging pendulum and alternating current. Alternating current is also an example of oscillatory motion because it repeats its cycle after equal interval of time. Periodic motion is the motion that repeats itself in equal interval of time. Now we need to know that periodic motion is so as to understand simple harmonic motion. First we should understand what is periodic motion. So periodic motion which repeats itself, any motion repeating motion, any motion repeat itself, any motion which repeat itself. After equal interval of time is called periodic motion. Now we will do that mass attached to a spring is simple harmonic motion. Mass attached to a spring is simple harmonic motion. Now we should verify this thing. Mass attached to a spring is simple harmonic motion. We verify mass attached to a spring is simple harmonic motion mathematically, and diagrammatically we will explain. So first I will explain diagrammatically. Now take a line like this. We'll draw a line like this. Let's say this is an object. This is called mean position. This is called mean position, equilibrium position. This is compressed. This spring is compressed. Now this is displacement x. This is displacement x. Now when force is exerted on this body is compressed. The spring is compressed and this force is stored in the body in the form of restoring force. So this is stored in the form of energy, potential energy. So when the spring is compressed, the restoring force is responsible for bringing body back to this original position. But when the force is acting on the body and it reaches the mean position, this is the extreme position. When it goes from position A to position O, at this point it will when it goes from extreme position to mean position, at that point the body will not stop. But it will try to continue its state of motion, because Newton stated that in Newton's first law of inertia, Inertia is the property due to which this body will try to continue its state of motion, will oppose any change of state, which opposes change of state. So due to opposition to the change of state, it will try to continue its state of motion. It will continue to continue its state of motion, and it will be stretched. This displacement will be equal to this displacement. So from this Hooke's state data, it will continue its vibratory motion according to Newton's law of inertia. Now according to Newton's second law, the force on this body is equal to ma, which we applied, and the restoring force is equal to minus kx. Equation B, ma is equal to minus kx. A is equal to minus k divided by mx. A is directly proportional to the displacement. Acceleration is directly proportional to the displacement. Now K is spring constant. And M is classical constant. So K divided by M is constant. So A is directly proportional to the displacement, and the negative sign represents directed towards the mean position. Directed towards the mean position. Now this is mass attached to a spring system. In this case, different position is shown in the pig. Now here the spring is compressed. This is the mean position. Here the spring is stretched. Here the spring is at mean position. Here the spring is at mean position. Here the spring is stretched. The spring will bring the body to the original position. Here force is 0 because at mean position. According to Hooke's law, F is equal to kx. So at this position displacement is 0. So force is 0. Here force is 0 because displacement is 0. At this point force will be maximum. Restoring force will be maximum. This topic is uniform circular motion and simple harmonic motion. Uniform circular motion describes the movement of an object traveling in a circular path. The motion of a body in a circular path is called circular motion. And simple harmonic motion, in which acceleration is directly proportional to the displacement. So in simple harmonic motion, acceleration is directly proportional to the displacement, and the motion of a body in a circular path. So we have to establish a relation between these two. Now a point P moving on a circular path with a constant angular velocity omega is undergoing uniform circular motion. Now its projection is vibrating about the mean position. So the the projection motion will be to and pro. This can be compared with the projection of the linear vertical motion of an oscillating mass on a on a mass spring system. So we should compare two types of motion. Mass attached to a spring with uniform circular motion. As you can see that both have same frequency. If both have a frequency is same, if frequency is same, both type of motion is same. It complete one vibration in a time in which it complete one vibration. So it is simple harmonic motion because in this acceleration is directly proportional to the displacement. This is also simple harmonic motion because in this acceleration is also directly proportional to displacement, and we have to derive it and we have to verify it. We have to verify, okay students? Okay, now next, this is also simple harmonic motion. It is the graph comparisons with this mass attached to a spring. This is also simple harmonic motion. The this show this is the motion of projection, and this is the motion of projection vertically. So both are simple harmonic motion. So we have to verify mathematically. We have to verify, and example show that the motion of a body in a circular path is uniform circular motion. So this is the motion, simple harmonic motion and uniform circular motion. Spring and waves behave very similar to objects that move in circle. The radius of the circle is symbolic of the displacement. Symbolically it represents displacement. Now first we will do for displacement. Displacement is the maximum distance from equilibrium position. So first I will draw a diagram. We have to verify that the motion of a body in a circular path is simple harmonic motion. Mathematically we have to verify. So our destiny is that acceleration is directly proportional to the displacement. Now here is a body and this is the center point. This distance is equal to radius. Now the body move from this position to point P position, from A position to point P position. So OA. From here I draw a point. The green line represents the motion of the projection. Represents the motion of projection. It is equal to x, and this distance is equal to the radius of the circle. Now we know that centripetal acceleration is equal to v square divided by r. V square divided by r. Now v is equal to a, as we know that v is equal to r omega. So centripetal acceleration is equal to r square omega square divided by r. R cancel. A is equal to r omega square. R omega square. This is the centripetal acceleration. Now we know that in the given diagram cos theta is equal to base by hypotenuse x divided by r, and we know that a centripetal acceleration or acceleration is equal to we just derived that r omega square. So its horizontal component will be equal to ax is equal to a cos theta r omega square into x divided by r is equal to omega square x, where omega is constant of proportionality, is constant. So a is equal to omega square x. So a is directly proportional to x if omega is constant. Now we can write this equation as, if it is directed from mean position, you will write omega square x. You will add, if directed towards, you will take positive. If directed away, you will take negative. So acceleration is directly proportional to the displacement. To the displacement and always directed towards the mean position. From this equation we can say that mass attached to a spring is simple harmonic motion, and the motion of a body in a circular path is also simple harmonic motion. Now we should now do this, derive the relation for the velocity of projection. Now we know that a particle at point P have two component of velocity, vertical component and horizontal component of velocity. Here vertical component of velocity will be equal to Vy is equal to V sine theta. V sine theta. As we know that, remember this relation. Sine square theta plus cos square theta is equal to 1, and sine square theta is equal to 1 minus cos square theta. Now we will write the relation sine square theta is equal to 1 minus cos square theta, and we already derived that cos theta is equal to x divided by r. Now sine square theta is equal to 1 minus x square divided by r. Now taking LCM, r square, here we will get r square minus x square sine square theta. Now sine theta taking square root is equal to under root r square minus x square divided by r. We already have taken the square root of this one. I will write again sine theta, when you take square root, sine theta is equal to r square minus x square divided by r. You will write this. Now put this value, the equation we have written before. Vy is equal to V sine theta. V is equal to r omega under root r square minus x square divided by r. So r is cancelled with r, and Vy is equal to omega under root r square minus x square. I will write neatly again. Vy is equal to omega under root r square minus x square. This is the final relation that we derived, where r is the radius of circle, r is radius, omega is the angular velocity. And Vy is the velocity of projection of a body moving in a circular path. Thank you, students. Next coming topic is simple pendulum. Simple pendulum. Wish you best of luck. In the next coming lecture, we will do simple pendulum. Thank you, students. Allah Hafiz.